Hello everyone. My name is Vito Faraci and I'm going to talk about magic squares. You do not have to be a mathematician to be intrigued by these squares. Although there is no magic whatsoever involved, when studied closely, these squares appear to have some magic about them. And hopefully you will agree after watching this video. Let's start with a formal definition so that everyone knows exactly what we're talking about. A magic square is simply explained, it's a n row by n column matrix where n is equal to 3, 4, 5, 6, and so on. As you know, a 3 by 3 matrix contains 3 times 3 or 9 cells. A 4 by 4 matrix contains 16 cells, a 5 by 5, 25 cells, and so on. By definition, each of the cells are filled with the numbers 1, 2, 3, 4, and so on, up to the number n times n. In addition, the numbers are strategically arranged so that each row, column, and diagonal will add up to the same number, which is called the magic number. So for example, the magic number of a 3 by 3 magic square is 15. Based on this definition, the smallest magic square known to man is a 3 by 3. A 2 by 2 magic square does not exist because a 2 by 2 matrix contains 4 cells, which must contain numbers 1, 2, 3, and 4. But no matter how you arrange 1, 2, 3, and 4 in the cells, the rows, columns, and diagonals will never add up to the same number. Try it yourself. So here we see an example of a 3 by 3 magic square. Take note, numbers 1 through 9 are arranged in such a way that each of the columns, rows, and diagonals add up to 15. Okay, let's now take a look at a much more interesting magic square, the 4 by 4. Now you will see some characteristics of a magic square that appears to be somewhat magical. The magic number for a 4 by 4 is 34. Now take a look at square number 1. Note that all the rows, columns, and diagonals add up to 34. In addition to the rows, columns, and diagonals, we have, the 4 by 4 exhibits other patterns. Take note of these patterns on the right here. I'll call this pattern 1, 2, 3, 4, 5, 6, and so on. Look at pattern 1 here. Pattern 1 says that these 4 cells will add up to 34. Okay, check it out. 17 plus 17, 34. And these middle 4, the 4 in the middle, will add up to 34. Also, these 2 plus these 2 add up to 34. Also, these 2 plus these 2 will add up to 34. Also, we have pattern 11, where we see these 4. All right, look at this. These 4 will add up to 34. These 4 will add up to 34. You see it? Interesting. Also, as we go through these squares, the first three squares will be true for all magic squares, all 4x4 magic squares. These three patterns will always be true. The other 9 will sometimes be true and sometimes not, depending on the square you're looking at. If you click the next square button, you will see another 4x4 magic square with the same magic number, but with a different number arrangement. So obviously, square number 1 is not the only 4x4 magic square that exists in nature, with 1 in the upper left-hand corner. So now the question becomes, how many other 4x4 magic squares exist with 1 in the upper left-hand corner? I found that question to be very difficult to answer and realized that it was a job for a computer. It turns out that there are 400 4x4 magic squares that exist, each with a different number arrangement. By continually clicking the next square button, one can view all 400 squares one at a time. While going through, while viewing, take note of the pattern characteristics of each square as shown by the highlighted patterns. The scan button can be used to scan through the squares so one can quickly get to the last square to determine the total count. Take a look. Here we see the program scanning through the squares, and let's see where it stops. Okay, so we have a message here that says reached last square with 1 in the upper left hand corner. Total squares equal 400. Okay, now we have seen all the squares with 1 in the upper left hand corner, and there were 400 of them. Now let's take a look at all the squares with 2 in the upper left hand corner. So to do that, we click enter 1 to 16 and enter a 2, and that will place a 2 in the upper left hand corner. And square number 1, here we see this is the first square that the program lists with 2 in the upper left hand corner. And we can play the same game with 2 in the upper left hand corner, and we can see how the patterns change from square to square. Now the next question is, okay, how many squares exist with 2 in the upper left hand corner? So to get that answer very quickly, we'll hit the scan button and scan through all the squares with 2 in the upper left hand corner, and let's see what we get. This time it's 396. 396 squares with 2 in the upper left hand corner. Okay, how about, let's say with 8, the number 8 in the upper left hand corner. How many of those do exist? I'll take a scan, and we see we can now examine all squares with 8 in the upper left-hand corner. And let's see, the program says, oh, look at this. 465 of these. Okay, so with this program, you can select in the upper left-hand corner any number from 1 to 16, and theoretically, you will have seen all magic squares, 4x4 magic squares that exist in nature. When you press the About button, you will see this page with some notes and background information. In particular, it states the fact that I wrote the math engine for this program back in 1977. And in all my years, I have found absolutely no practical use for these magic square programs, or even the magic squares themselves. However, they happen to be very intriguing and brain-teasing. Try putting together a 4x4 magic square from scratch without referring to this program. It can be very challenging. Then try writing a 5x5 or a 6x6. I guarantee you'll have a lot of fun. I hope this program not only provides a little entertainment, but also some interest in magic squares themselves, and a little bit of insight of how mathematics is full of order and patterns. When you press the Earl button, you will see this page. Just copy the Earl into your browser and you'll be able to run this program on your computer. Also find my email address. I would love to hear from you. If I find that there is a public interest for this type of magic square program, I would be motivated to write the 5x5 and maybe even the 6x6. Okay, thank you for watching, and I hope you enjoyed this program. Bye-bye.